This webcast talks about energy, how it's stored, and a visual tool for examining energy called an energy pie chart. So first of all, let's just talk a minute about what is energy. You know, when you say someone is full of energy, or you know that when you fill a car up with gas, it now has energy that it can use to go places. So energy is the capacity for being active, the capacity for doing work, and it's also, I want you to come to think of it as a reason that things change. If you come to school and you're standing in the junior lobby and then you go upstairs to the biology lab, you do work on yourself, right? You spend energy to take yourself up the steps. So the change is that your height, your position above the earth has changed. And the reason that you were able to change your height is because you had the energy to do that. Okay, so energy is a cause of change. Energy is conserved, which means that it might move around, but it's not created or destroyed. Okay, so it's a conserved substance. It has a substance-like characteristic, which means that it can move from one object to another. Just like water flows from one container to another, energy can move from one object to another. And energy, again, has the capability to produce change in physical systems. In fact, we use energy as a measure of the ability to produce change. And so if you watch a system and look at what changes it's going through, then you can identify the means of energy transfer and storage in that system. Now, in our common language, we frequently refer to different forms of energy as if they were something different, right? We might talk about chemical energy in a battery, or nuclear energy, or things like that. But really, what we are talking about are different ways of storing energy. In fact, energy does not come in different forms. Energy is energy is energy. The energy must be stored in a physical object, and what we are really talking about is the way that that energy is stored. So when we talk about kinetic energy, that's energy that's obvious because of the object's motion. Or gravitational potential energy is energy that's stored by the object's position above the earth. Things like that. So, try to remember that really all of these energies that are stored in different methods are in fact the same thing, right? So energy does not come in different forms. Energy must be stored in a physical system, but it can flow and transfer either within the system, it can be stored in different ways, or it can move from one object to another. So energy can move. It's conserved, and that means that energy can move, but it's never created or destroyed. There's a given amount of energy. As it moves between storage modes, so that it's stored differently, or even if it moves from one object to another, it causes changes that you can observe. But even after it moves, it is still energy, okay? And so we should be able to track where it is. And energy is measured, the metric unit for measuring energy is called a joule, which is represented by an uppercase J. Okay, energy is measured in joules. When the more energy that gets transferred, the more change you can see in the system. So if you think about a rubber band, if you stretch the rubber band just a little bit, it might move a few inches when you let it fly, but if you stretch it all the way, it may fly all the way across the room. So the larger the stretch, if you will, of the rubber band, the more motion that you can see when you release it. So, and by stretching the energy, the rubber band, you are transferring energy into it. So more energy transferred, you see more change. There's a pretty useful analogy between energy and money, because money, like energy, can be stored in many different ways, right? You can put it in your wallet, you can put it in the bank, you can put it in you can buy stocks and bonds with it in an investment account, things like that. And money can be exchanged. Your personal money can move between different storage modes, right? You can take money out of a piggy bank and put it in your purse, and then you can take it from your purse and put it in a bank. So it's still your money, but it's just transferred to different places. You can also give your money away, right? So then money would be transferred between your system and some other person's system. But as the money is moving around, it basically is still the same thing, right? It's still US dollars, whether it's $1 in your purse or $1 in your bank account or $1 that you gave to someone else. So in all those ways, it's very similar to what we've been saying about energy, because energy is also stored in many different ways, and it can be moved between those storage accounts and also can move from one object to another. When energy is stored in an object, it's stored as internal energy. And so whenever the amount of energy in the system changes, and that could either be by moving between storage modes within the object, or it could be transferring from one object to another. But anyway, when the amount of energy in the system either changes or just redistributes, you're going to be able to see some physical changes. Maybe the height of the object will change. Maybe its speed or its temperature or pressure or volume. All of these physical things that you can observe help identify how the energy redistributed. We're going to be talking about mechanical energy, which is the energy due to things moving or changing shape. And so there will be 3 forms of mechanical energy that we will discuss. And I'm going to start by giving just a brief description of each one so that you can start to recognize them and talk about them. So the first is gravitational potential energy. That's represented by an uppercase E for energy with a subscript of G for gravitational. Gravitational potential energy is energy that an object has because of its elevated position. That means its position above the ground. So some examples would be a ball that you're holding over your head, or water in a big elevated reservoir, or a squirrel that's sitting on a tall branch. All of those things, because they are high above the earth, they have some gravitational potential energy. So our typical convention says that when an object is on the Earth's surface or on the floor, for example, that it has 0 gravitational potential energy. And then the higher the object moves, the more gravitational potential energy it has. So changes in height identify changes in gravitational potential energy. Kinetic energy is represented by an uppercase E with a K subscript. And kinetic energy is energy that is stored in an object by virtue of its motion. So if the object is not moving, then it has no kinetic energy. And as the speed increases, the kinetic energy increases. So you recognize kinetic energy by how fast an object is moving. If it's not moving, it has no kinetic energy, and then the faster it goes, the more kinetic energy it has. The third type of mechanical energy is elastic potential energy, which is represented as uppercase E with a subscript of EL for elastic. When an object, such as a spring, undergoes a temporary deformation, then it is storing energy elastically. A deformation means a change in shape. So for example, a spring, in this picture there's a little coiled spring. You can stretch it. You could also compress it. But when you change its shape, it's a temporary change, because as soon as you pull your hand away, it snaps back to its original shape. So that's important. In order to store elastic potential energy, an object has to be able to return to its original shape as soon as, whatever's happening to change its shape goes away. And so anyway, so you'll recognize elastic potential energy if you see something like a spring, or a rubber band, or a bungee cord, something like that, that can be stretched or compressed and then will return to its original shape. There's one other type of energy that we want to be able to recognize. This is really not a mechanical energy, but it's called dissipated energy, and we'll write it as uppercase E for energy with a subscript of dis, D-I-S-S. So some energy storage modes are dead-end storage modes, meaning that once energy has been moved to that storage mode, you cannot get it out for useful work. And so EDIS represents unrecoverable, unusable, microscopic kinetic energy. The reason I'm saying microscopic is because what happens, think about when you rub your hands together really fast. Your hands, you can feel them heating up because of the friction between your palms. That heat that you're feeling, it causes the atoms and molecules on the surface of your hands to move, to vibrate faster. Okay? And so it's a kinetic energy, but it's at a microscopic level. And it's not really useful for making something move or lifting something up. So you know where the energy has gone when you rubbed your hands, but it's not something that you'll be able to get back to use for something like climbing the stairs or lifting a box. Okay? So EDIS is unrecoverable, unusable, microscopic kinetic energy. Most commonly, we will talk about energy being moved to the dissipated storage mode because of friction. But other mechanisms might be something like a very bright light or a loud noise dissipating some energy. Okay, so to recap, we now know about 4 energy storage mechanisms. There's gravitational potential energy, where energy is stored by virtue of its location above the Earth. There's elastic potential energy, which is due to a reversible deformation of an object. There's kinetic energy, which is energy due to the motion of an object. And there's dissipated energy, which is unusable and unrecoverable. Okay, so we've talked about how energy is stored in an object as internal energy, and the change in internal energy of a system equals the sum of the changes in all of the various storage modes. Okay, so we've mentioned 4 storage modes. Those are the only 4 we're going to talk about, but there's the kinetic, the gravitational, elastic, and dissipated energy storage modes. And so if there were changes in the amount of energy stored in those modes in the object, then maybe the total energy of the object would change. the important thing to know is that in an isolated system, that change in energy is always zero, right? Because if the object is isolated, there's no way for it to interact with another system, either to receive energy transferred in or to transfer some of its own energy out. And therefore, at the object's level, there can't be a change in energy. And so that means that if one of the modes increases, then another of the modes, the level of energy has to decrease. So if kinetic energy increases, for example, maybe gravitational energy falls, but the sum of them has to stay the same, because at the system level, there can be no change in energy if the system is isolated. And so we're going to start using a tool called an energy pie chart to analyze how energy moves around within isolated systems. So the pie is a circle that represents the total amount of energy, and it stays the same because energy is conserved, right? It's not created or destroyed, and if there are no transfers of energy into or out of the system, then the amount of energy stays the same, but the pieces of the pie might change size because energy may move from one type of storage mode to another. So I'm going to go to worksheet 6C and do a couple of examples here. So I'm in worksheet 6C. So first let's think about a rubber band, because we've all shot a rubber band before. When you first, just pick up a rubber band or it's laying there on your desk, it's not stretched, taut, it's just very relaxed and it has kind of a funny shape. It has no real mechanical energy. It's not moving, it's not storing any energy. That's the state. So there is no pie. But then someone takes it in their fingers and they stretch the rubber band taut. So it took someone to pull on the rubber band. So there was a transfer of energy. And now there is a pie of energy, and I'm going to represent it with this circle. And right now, all of the energy in this rubber band is stored as elastic potential energy. The rubber band is not moving, so there's no kinetic energy. And I'm kind of ignoring the height of the rubber band because I'm going to say that the height does not change. So let me just go ahead and say that. Assume that the height of the rubber band does not change. Okay. And so really, at the beginning, all of the energy in this rubber band, it's stored as elastic potential energy because the shape has changed, but it's a reversible deformation. When you pull your finger away, the rubber band goes back to its original shape. And so you pull your finger away, and then all of a sudden you see, it's not stretched taut anymore, but it is moving through the air. Oh, I should have drawn it up here. I'm sorry. It's moving now. And so the energy in that rubber band is still there. But now there's no more elastic potential energy because it's no longer deformed. And now it is moving. And so now that energy has changed flavors. It's now kinetic energy in the rubber band. Okay, so we saw change in the shape and the motion of the rubber band, and we can explain that shape by identifying how the energy is stored in the rubber band. Let's do another one. So here is a pop-up toy, and I think I have a video that I'm going to show of the pop-up toy. Let's see. Here we go. So this is just a little spring toy. That will jump in the air. So there's the spring, and when you press down on the toy, it compresses the spring, changes the shape of it, and in a couple of seconds, ooh, the spring returned to its original shape, and it pushed the toy up. Okay, so that's what we're going to do now, is talk about that pop-up toy. So here's the spring, and initially it's compressed. We'll talk about that A. The spring is pressed down. Okay, so, and at that point, it is on the ground, right? It's on the ground, and so there's no height, and so really all of the energy in this little toy is stored as elastic potential energy because it's on the ground and it's not moving, but the spring is compressed. Then, and the toy is going to go up and then come down, right? That's going to be its trajectory. At B, we're going to see the toy as it's moving up in the air. The spring is not compressed anymore, it's relaxed, but the toy is moving. Here it's not moving. Okay, and it's higher, right? It's not on the ground anymore, it is higher. So there's no more elastic potential energy because the spring is not compressed. But we have the object almost at its peak, so it has a lot of gravitational potential energy because it's higher, and it has some kinetic energy because it's moving. Then at C, it's here at the peak, and the spring is still relaxed. It's not moving, right? Because at the peak, for an instant, the velocity is 0. And so there's no kinetic energy. Now all of the energy in this toy is stored as gravitational potential energy. And then after it passes the peak, it starts falling down. And then we're looking at it right before it hits the ground. This is D. So it's moving very fast because, it speeds up as it falls. The height is essentially the ground, right? It is just a millimeter, let's say, before it hits the ground. And so I'm not going to show any gravitational potential energy because the height is almost 0, but it is moving fast, and so it's kinetic energy. By the way, I know my pies, I'm not able to draw them perfectly the same size, but I'm trying. Okay, but what we're showing here is the progression of how the energy is distributed in this little pop-up toy as it's from the time when the spring is first compressed and through its trajectory.